Hi, good afternoon everyone. So today we will be presenting the lab report of the experiment 9 and 8, which is analysis heating and cooling systems. So the group member is Trisha, Alia and me, Alicia. So we will dive into the detail about our analysis and findings. So I will continue for the part introduction. Humidity represents the quantity of water vapor present in gas. Typically, it's measured as the mass of water vapor per unit mass of dry air, divided of specific units. This property is delineated into various forms: absolute humidity, which denotes the volume independent amount of water vapor in a given air volumes. Relative humidity, which compares to the actual water vapor content in the air to its maximum capacity at a particular temperature, expressed as a percentage. To gauge humidity in this study, a dryer unit and heat will be utilized for measurement process purpose. The experimental procedure involves the measurement of both dry bulb and wet bulb temperature, followed by the utilization of a psychometric chart to ascertain the enthalpy. Additionally, to determine total energy and perform water mass balance, a Morse code will be employed in the investigation. This multifaceted approach aims to comprehensively evaluate and understand the characteristics of humidity through diverse measurement technique and analysis. Our experiment focused on to examining information derived from the thermodynamic operation involved heating, cooling, and the process of increasing humidity. To begin, let's dive into the our setup and methodology for the experiment. So we have four procedures. The first one is for heating process. The computer was powered up to initiate operation. Prior to commencing the process, all measurements were documented. The fan was activated and left running for a duration of 5 minutes. At SVI, the preheater was activated and permitted to operate for 10 minutes. This procedure was replicated by modifying the temperature setting. Subsequent to completing the experiment, the preheater was switched off. For the cooling process, the air conditioning system was activated with the compressor reaching an A1 value near 0 degrees Celsius. The blower was switched on and reached at a stable state within 10 minutes. The air flow rate was notably raised. The experiment was replicated using a different air flow rate. All readings were meticulously documented. Next are for the part of the procedure 3 and 4. Procedure 3, which is the humidification process, activate the humidifier using both the control panel and unit. Confirm that both components are in operation. Switch on the blower until it reaches a stable state. The readings noticeably rose as the airflow rate increased. Repeat the experiments during a different airflow rate. Turn off the blower upon the completion. The next one is for heating, cooling, modifying, and reheating process. Prior to initiating the process, all measurements were documented. This involved incorporating all unit operations into the procedure. The procedure was activated until E1 reached approximately 0 degrees Celsius. The humidifier was activated and allowed to run for a short duration. The air flow rate was modified by activating the blower. Both the preheater and reheater were activated for 10 minutes duration. This led to an increase in the temperature of the air-water vapor mixture. The readings were taken and recorded. To compare values, the experiment was repeated twice with verifying airflow rate. Finally, the compressor, humidifier, reheating, and blower were deactive. That's all from the methodology.
M dot represent the mass flow rate, Q represent the heat flow rate, and H represent enthalpy. The subscript I and O denote that the inlet and outlet state, and also W will be the absolute humidity. In this experiment, a psychometric chart is used to determine the properties of moist air. The psychometric chart illustrates the relationship between dry bulb temperature and also the absolute humidity. It also displays the relative humidity, wet bulb temperature, and sometimes the enthalpy and specific volume of the mixture. Psychometric is the study of the thermodynamic properties of air water vapor mixture with a particular emphasis on the relationship between temperature, partial pressure, and enthalpy. Hi, I'm Trisha. I'll explain about theory and working for this report. First, we use the simple heating by raising the temperature, cooling by lowering the temperature, humidifying by adding the water, and also dehumidifying by removing moisture are the procedures used in this experiment. The air water vapor mixtures, heating and cooling processes via air conditioning processes are examined in this experiment. The steady flow conservation of mass and energy principles can be used to represent these. First, we will use the dry air mass, water mass, and also the energy. To conduct this experiment, several methods use and also to analyze the effect of heating, cooling, humidification, and reheating of our air. First, change the air temperature to that is applied to the area while maintaining a steady air flow rate. This is the fundamental variable temperature and constant volume method. Second, change the rate at which the air supplied to the space flows while maintaining a constant temperature. This is the constant temperature variable volume method. Lastly, turn off or on the blower to check the air flow rate relationship with temperature and humidity. The air flow rate, enthalpy changes, temperature of the wet and dry bulb, absolute humidity, and the necessary heating and power are the primary parameters we focus in this experiment. This is the example diagram for psychometric chart. We use two constant given and we get all the variables through it. As for this result and discussion part, there will be few raw data displayed, and this will be for heating process where we will change the preheated temperature, then we will change the air flow rate. This is the raw data obtained for cooling process where first we will get data for before turning on the blower, and then the second table will be after turning on the blower. Then we will also change different air flow rate. This is the raw data obtained for humidification process where we will use the same procedure we used for cooling process. As the last experiment, we will get raw data for heating, cooling, humidification and reheating process where we first turn off the blower and then we will turn on it, and then we will try to also change the air flow rate. From the raw data obtained previously, we will try to process it more detailed through the relevant properties obtained from the psychometric chart, where we will use specific volume, enthalpy of humid air, and also wet bulb temperature, where we will get the mass of moist air, the mass of dry air, and we will finally get energy load through energy balance. We will also use that energy load to get the specific heat capacity of air. This shows the result for heating process. These will be the calculated data as in for enthalpy of humid air, mass flow rate of water vapor in air, energy load and specific heat capacity for before and after turning on the blower, and also for different air flow rate for cooling process. So, as in for humidification process, this is the calculated data. First table shows the result of enthalpy of humid air, mass flow rate of water vapor in air, energy load, and specific heat capacity of air before and after blower turned on. And also, table 14 shows the result of enthalpy of humid air, mass flow rate of water vapor in air, energy load, and specific heat capacity of air at different air flow rate. Lastly, the same steps for humidification process will be applicable for the last procedure where we do simultaneously heating, cooling, humidification and reheating process. We will get enthalpy of humid air, mass flow rate of water vapor in air and also energy load for two different states where first we turn on the blower and then we will turn it off, and then for different air flow rate. Okay, so that's for result. Now we'll continue discussion. For heating process, the experiment yields the relative humidity of the air and the temperature of the dry bulb, which are used to calculate the enthalpy of humid air. The psychometric chart, which will be shown in figure 1, can be used to define the enthalpy of humid air and was used to determine the specific volume of air. Then, the data was used to compute the mass flow rate of water vapor in air. The preheater's temperature and the air flow rate are adjusted during the heating process to conduct the experiment. Table 1 and 2 displays the collected raw data. The same table illustrates how the temperature of dry bulb rises in proportion to the relative humidity of the air when the preheater's temperature rises from 30 to 40 degrees Celsius. The energy load rises in direct proportion to the increase in preheater temperature. This is due to the fact that air's capacity to retain moisture rises with temperature. The relative humidity also increases when the air flow rate drops from 4.4 meter per second to 3.6 meter per second, while maintaining the preheater's temperature at that level. This is because the air's moisture content drops as a result of decreased surface contact between air and water caused by the preheater. When the air flow rate decreases during the heating process, the energy load usually rises because of slower heat dispersion and decreased heat transfer efficiency. The temperature differential between the air and the heating element tends to rise as the air flow rate drops. Heat transfer is fueled by temperature differentials. Higher heat transfer rate may result from wider temperature differential, but maintaining the desired air temperature will need more effort from the heating element. Now we will continue for the cooling process. By turning on or off the air blower and varying the air flow rate, the experiment's data is collected. The psychometric chart in figure 1 can be used to define the enthalpy of humid air in order to compute the mass flow rate of water vapor in air. The specific volume of air was also calculated using the psychometric chart. Table 3 and 4 displays the raw data collected. It was also assumed that the moisture content increased at the average dry bulb temperature when the blower was turned on from off, as indicated in the table. The experiment's findings show in Table 11 and 12 that when the blower is running, the enthalpy of humid air drops as air temperature drops. Because warmer air can hold more air moisture, the mass flow rate of water vapor in air also decreases as air temperature drops. So does the amount of water vapor in the air. The air moisture content rises when the air flow rate goes from 3.6 meter second to 4.5 meter second. In theory, a higher moisture removal rate should follow from an increased airflow rate, while the cooling process has lower enthalpy than the heating process. The energy load increases with an operation of blower but decreases as there is an increase in airflow rate. The energy load may drop during a cooling operation if the air rate rises because of better cooling performance and increased heat transfer efficiency. The temperature differential between the air being processed and the cooling element can be reduced by higher airflow rate. Reduced temperature differential indicates less effort is required from the cooling element to transfer heat, which would result in increased efficiency and decreases the use. As though when we look for humidification process, the process of humidification involves introducing moisture into the atmosphere. Throughout the experiment, the temperature is kept constant, but the outcome is examined by turning on or off the blower or increasing and decreasing the effort. Table 5 and 6 displays the collected raw data. The table illustrates how that when air blower is turned on, the air's relative humidity drops. This is due to the humidification system's water evaporation rate could be accelerated by the air blower. The total humidity level may drop if the pace at which moisture is introduced to the air is greater than the rate at which water vapor evaporates or may due to malfunctioning of humidifier. The energy load increases when the blower turned on as the blower requires electricity to run. When activated, it speeds up airflow throughout the system, distributing the humidified air to the various areas of the room. The total energy load is impacted by this higher fan power. The energy load also decreases as the air flow rate decreases from 4.3 meter per second to 3.6 meter per second because less air passed through the humidifier, decreasing the amount of air contact between the moisture in the air and the air. In general, lower airflow rate results in less heat loss in the humidification system. Less heat loss from less heat loss from slower air movement through the system could mean less energy needed to keep the temperature where it is. Let's go to the last part. Every step of the heating, cooling, and humidification process are involved in the experiment. Table 7 and 8 will show you the raw data collected. The result in table indicates that when the blower is turned on, the air temperature rises and its relative humidity falls. This is because, in contrast to cooling and heat humidification, the heating process requires more participation throughout the entire experiment. The energy load also increases with the operation of blower. This is because by enhancing air circulation and distributing the condition air around the room, turning on the blower helps. Effective cooling, heating, and humidification depends on this, but it also needs more energy to run the blower. System that incorporate temperature control mechanism to maintain precise temperature set points also need more energy when several processes going on all at once. To coordinate and balance the numerous processes, the control system must exert more energy, which is also more effort. However, as more air passes through the heater, raising the air's temperature and increasing the enthalpy of humid air, but the energy load is decreased as the air flow rate increases from 3.8 meter per second to 4.4 meter per second. Both the temperature and enthalpy of the air tend to rise when the air flow rate is raised during a simultaneous process that includes heating, cooling, humidification, and also reheating. First, more efficient heat transfer mechanism result in more effective heating and humidification due to the higher air flow rate. Due to the increased heat and moisture content in the air, this causes a larger enthalpy rise. Furthermore, a higher temperature rise can be encouraged by reducing heat losses by shortening the air's resistance time in heat exchange components due to the increased air flow rate. When heating, cooling, humidifying, and reheating are all being done at once, an increase in air flow rate may result in decrease in energy burden for a number of reasons. First, the temperature changes are made possibly by more effective heat transfer process, which are facilitated by higher flow rate. Secondly, by enhance the performance of heat exchange components, the higher flow rate may indicate less energy requirement.
Okay, so I'm Alia Inani binti Mama Anwar, and now I will proceed the presentation with the conclusion. So, in conclusion, this experiment apply demonstrate the use of psychrometric charts by demonstrating the determination of numerous fluid properties, including specific humidity and volume, using only two variables, which is the dry and wet bulb temperatures. Consequently, moist bulb temperature is lower than dry bulb temperature. Air in temperature is higher than air out temperature, as demonstrated by this as well. As a consequence of this experiment, the wet bulb temperature rise and little heat is lost into the air when the air has a high water content. Furthermore, the wet bulb temperature rise with increasing air moisture or water vapor content. In order to determine the refrigerant state after a specific progress, it is also crucial to use the pressure against enthalpy graph. This conservation of energy principle is followed by the air conditioning cycle. For the recommendation, first of all, correct readings can only be obtained by taking values after they have been held in a stable state. The second one, at least two further repetitions of the experiment are required to guarantee accurate result. And these are the references that we use to complete our lab report. So that's all from our group. Thank you for listening.